I'm glad to introduce the first speaker of the second last talk of this wonderful workshop. So Antoine Chambert-Loir will speak about integral points of bounded height on toric varieties, reloaded.
Okay. No, it's okay. So thank you very much for being here. Thanks to the organizers for the invitation. The reason for the last word of the talk is that I made a similar talk with the same topic 10 years ago in front of maybe all the previous audience is there today. And this talk has suffered many, well, the paper related to the talk has suffered many things in between. And in fact, it's clear that it is still a work in progress. I plan to bring a construction hat and something. So this reloaded is to say that so it's a second try, and probably there will be a third one, but I hope it would be enough then. So I'm interested in counting and distribution of integral points of bounded height on toric varieties. And so this is joint work with Yuri Tschinkel and with help from Florian Wilsch. The model for our work is precisely the Manin's conjecture for rational points. So let me just recall the kind of what I mean with Manin's conjecture, because we are not only interested in taking a given toric variety and proving asymptotics with a precise constant and so on. I'm not really interested in a single one. What I want to understand is to give a structural behavior for the number of points. So I want to express I want the result to be valid for a large class of such toric varieties, and the constant to be expressed in terms of the geometry or the arithmetic, Galois theory, volumes, and so on. So in general, the Manin conjecture, you take a projective variety of a number field. The case of function fields is equally interesting, but will not be discussed here. And you assume that it is smooth or smooth enough so that you have a canonical line bundle. And this canonical line bundle gives rise to the height function. So in general, height functions are not fully determined by a line bundle. They are only determined up to a bounded function. And so if you expect to give precise asymptotics, you need to say how you chose your height function. So the framework I'm used to comes from Arakelov geometry, and we will consider this line bundle to be equipped with an adelic metric, which means that for for all places V of f, we have a norm function on the sections so whenever I have a section on an open subset, I'm allowed to speak to speak about its norm, which will be a real valued function, positive, and there is a usual calculus for norms on vector spaces. So if I multiply a section by a function, the norm of the product will be the absolute value of the function times the norm of the section. I want to study the points. Sorry? L is kx here. So it could be L, it could be another line bundle. Here it's kx. And so the height will be anti-canonical, so it will be minus kx. And so you expect that there are reasons so that you are able to count the number of points of anti-canonical height smaller than something. And so you will assume that kx minus 1 is big enough. So we assume that kx minus so you assume that it is ample, or here big. And big means that it is a sum of an ample line model plus an effective one. And this gives more examples and are equally interesting. For example, all toric varieties are of this form, or all proper toric varieties are of this form. Projective, say. Okay, and so then what we expect, so there exists a bad locus, say y inside the rational points, such that for all B, the set of points outside of the bad locus of height smaller than B is finite. And its cardinality, so this set could be, I will call it x prime of FB. And if you write n x prime of B to be the cardinality of this set, we expect that this is something like a constant times a power of times B, in fact, times a power of log B. And in all current examples, so the goal now is to specify C, T, and Y. So T is supposed to be the rank of the Picard group of X, which is supposed to be finite. And C is a product of various quantities. So there is a rational number which is related to the geometry of the effective cone. in the Picard group of X tensor with real numbers. There is a cardinality usually of the first cohomology group, Galois cohomology group of F with valued in the Picard group of the variety over the algebraic closure. And there is a volume term. Sorry? No, so the K. F is a number field, sorry. Sorry? No, there is Kx, but there is no K, I mean. So in fact, the details of this work are full of analysis, and then K is for compact sets. That's why I chose F. And then there is a volume of a suitable subset of the adels of the adelic points of X. So they are the adels of F with respect to a Tamagawa measure defined by pair. And suitable in practice is something like the locus where the Brouwer-Manin approximation vanishes. But it could be something else if something new, if some new obstruction appears, then people will be ready to change to change that part. And so I'll be quick on that. But so X is projective. So X of AF is a product of X of X of FV for all completions of the number field F. And so basically to define a measure, you need, so it would be tau, and the measure will be a product of local measure tau V, a measure on each V. But, and there is a natural way to define tau V, because to define tau V, you can just take any n form if n is dimension of. You take any local n form and you divide. You take the measure it defines on the analytic variety, and you define by the norm with respect to the V-adic metric. So this is a kind of Lebesgue measure defined by an n form, and this is the norm of the n form. And if you do that, it does not depend on the choice of the local n form, just by homogeneity of norms. And so you have a local measure, which is very natural. But if you do that, you cannot take the product, because the volume of X of FV is close to 1, but not so close. It's 1 plus something. And so the product diverges. So you need convergence factors. And the one defined by Emmanuel-Peyre are related to the local L factor of the L function at 1 for the Galois group acting on the Picard group of the variety on the algebraic closure. And then if you add convergence factors, usually you put some corrective term to combine. So usually, so pair multiplies by the inverse of the global L function at 1, which deprived from this vanishing term. So it starts the residue or the leading term of the global L function. And so this is the kind of volume that you expect. And for toric varieties, it worked, and it worked for many other varieties. And I want to say something new other is to understand to explain the word distribution, and I'd like to keep the blackboard here for the moment. So distribution means, for me, how do the points of bounded height, so how does this set x prime of fb distribute inside this adelic space? And one remark is that in the closure of the set of all rational, the support of the Tamagawa measure will contain will contain the closure of the set of the rational points. And more precisely, what Peyre has shown is that if you can prove such results for not only a given height function given by the embedding of the choice, but for any height function, then you have something which is, in my sense, much more interesting than this counting result. You have a precise equidistribution result for the points of bounded height. So if you can prove this kind of result for any height function, you can prove that the Dirac type measure which is just a sum of masses at all rational points of height smaller than b, divided by this number, nx prime of b, converges to the measure tau, to some measure, to some probability measure, which is constant time. And you get this. So if tau is maybe tau restricted to the restricted to the stable subset. Yeah.
I think your convergence factor is probably on the inverse.
Probably. Yeah. Right. In fact, I never know whether I put lambda v minus 1 or lambda v. So, but it's better to write LV minus 1 for a reason I explained when I switched. And the subset is the one you found in here.
In that case, you mean the closure of the...
Exactly. So if you do that, for example, for toric varieties, you prove by the method I'm used to is analytic number theory and Fourier harmonic analysis. You prove that the closure of the rational points is the locus of the Brauer-Manin, where the Brauer-Manin obstruction vanishes. You get it for free, for free. Nothing is free in this world, you know. So let this get up. James Brown, you say get up.
Green.
Sorry?
Green. There.
There. Sorry. And there is something else I wanted to say, but sorry, I won't write it on the blackboard, which is what is the bad locus? So for some varieties, there is no bad locus. For example, if you can do this on projective space or on Grassmannians and so on, then you can prove it with y prime is empty. For toric varieties, the people are used to take for the bad locus the complementary subset of the torus. And in general, there are varieties for which you are forced to take a bad locus. And at the beginning of the theory, it was expected that this bad locus would be the rational points of a Zariski closed subset. But now it is well understood since work of Batirev, Tschinkel, their first counterexample to this initial expectation, and then work of Le Redulier, and then now by the geometric results of Lehmann, Tanimotos, and Gupta, that it is reasonable to expect this with taking y prime a thin subset in the sense of the Hilbert irreducibility theorem.
In general, one does not know what
No. So initially, people proved results with Zariski closed subsets. Then there was the Battireff and Tschinkel found a counterexample. And well, there was a bad locus that you needed to remove if you wanted to have the expected asymptotics. And this bad locus was a thin subset. And it is very dreadly to say, okay, remove a thin subset, because you don't know what you are ready to take away with. So, but then now we have this geometric results that in principle there are finitely many. So there is a very precise thin subset which is defined geometrically that you are expected that it is enough to remove. So, but now the field needs people to prove the result, the corresponding result. So, which is so for a case which is very close to the counterexample of Battireff and Tschinkel, which was a family of cubic surfaces, but for the similar family of conics, maybe, or I don't remember the dimensions. There is a result by Browning and sorry, yeah. So Browning and other people, but I did not make my homework correctly enough, so I don't remember the other authors. Where is Jim? Who should we credit for the? Hisbron. Okay, so Browning and Hisbron. Sorry. So in this case, the theorem is an example where it is proved that if you remove the bad locus, you get an asymptotics as predicted by this blackboard. So what about integral points? So then the picture is similar, because you will take U inside X Zariski open subset. And U will be a flat model of U over OF. So a scheme of finite type and flat over OF, which with generic fiber U. And then the question is restrict the counting problem to the integral points of U. Except that we will change the counting problem, and usually it is more natural, many theorems in algebraic geometry show that if you are interested in open varieties, not non-projective, it's more natural when you want to understand the positivity of the canonical line model to look at the log canonical line model. So usually U will be X minus D, and D will be a divisor with normal crossing. So the fact that it's precisely a divisor with normal crossing is not so important. But we will look at the log anti-canonical line model will be Kx minus 1 of minus D. And this is with respect to this line model that we want to look at the height, and which is assumed to be big again, because otherwise there is no hope. Sorry? So there are two minus signs. So I should have given an example. So if X is Pn, and you remove, you take for D a hyperplane at infinity, you will have Kx minus 1, which is O of n plus 1, and Kx minus 1 of minus D, which is O of n. And just to take, if you take f equals q, then u will be the u is an. If you take the usual model of an, we are just counting the points of z to the n of bounded height, and you know that there are roughly b to the n. And so the exponent n has something to do with this n here. That's why we switch. And so it's interesting to look at what happens in this case of Pn, because if you look at the similar so we will expect some asymptotics of this form, constant b powers of log b. But it's not at all clear what T and C are, and they are, the formulas that we get in some cases are much more complicated than just a product of. But what happens is we get volumes of so adelic spaces. So we get the volumes of the integral points of u inside the u of f inside the finite adels, and so we will need a measure on this adelic space, and we get also volumes of components of intersections of components of d of fz. And this is something that appears already in this simple case. If you take the sum over all x in z of absolute value smaller than b of delta x, so if you count this, if you take 1, so you get 2b plus 1. So it's roughly a constant times b. But if you take sum x in z absolute value of x smaller than b delta x, and we divide by the number of points, this is a natural measure on the adelic space. But if you look at its projection on the real set, so you look at this measure on P1 of R, it's very easy to show that it converges to the Dirac measure at infinity. So at the Archimedean place, there are phenomena which are quite strange. It is those limit measures of points of bounded height. They converge to the boundary. And that's life. So. And so we need to we need to take care to define such volumes. And so in fact the first remark we had made with Yuri in a paper published in so it was in a so we need Tamagawa type measures in this context. And so this is done in a paper with Yuri, in a paper published in a review called Confluentes Mathematici. And then there is a convergence factor. Which we take the Euler-Poincaré virtual Galois module of U, which is H0 of U F bar GM modulo constant. So these are the invertible functions on U over the algebraic closure, modulo constant functions. And I assume that U is geometrically connected in the setting, minus the same thing for H1. Maybe EQ, we can. And so this is EP for Lapin-Carré, but also for Manin-Peyre, as you guess. And this virtual Galois module gives you the correct convergence factors by taking L functions. And with this formula, it's nice that if you take semi-simple groups, if U were a semi-simple group, then this is 0 and this is 0, and you get the classical fact that you don't need convergence factors for semi-simple groups. But if it's a torus, for example, you know that the convergence factor by the theory of Ono is only given by the characters of the torus, and then you have no H1. So this is a formula that interpolates between the classical Ono formula and the formula of pair. And so this is this will take care of measures on such adelic spaces. And to have measures on D of FV, we will use the residue theorem. So this is a theory of either the residue theorem with the adjunction formula or whatever. Or the theory of Le reforms. It's an equivalent way. Namely, that it's just a kx, kd is kx of d restricted to d. So if I restrict the log canonical line bundle on the divisor at infinity, at least if d is smooth, then I get the canonical line bundle, and one can explain how to get metrics on what we have. So there are natural measures on. So this is the general picture. So now the goal is to, no, and there is yet another thing to explain. Because many people told me it was hard to understand it in our paper. Which is this business of Clemens complexes. So I've shown you by an example on Pn that if you the points go to infinity, the distribution of points goes to concentrates along the divisor at infinity. But sometimes you have two components, and then the points are used to concentrate on the intersection of the two components at infinity, the accumulates. So there are also Clemens complexes, and so then we take D will be a sum of alpha in some set A of divisor D alpha. And we take a simplicial complex with vertices the alpha such that D alpha of FV is not non-empty. So it will be Clemens V of XD, something like that. And generally, faces are subset A in A. And plus irreducible component of, no, let's assume that it has strict normal forcing. And so faces such that intersection of this D alpha is non-empty. So we only look at, we take the usual simplicial complex of the boundary, but you restrict it to the parts which have FV rational point, FV points. Otherwise, are not supposed not to give anything in the. And after all these preliminaries, which are more or less the business of the paper in confluent test that I quoted earlier, we were ready to to look at two cases, which can, respectively, should be amenable to the Fourier-theoretic methods, namely equivariant compactification of vector groups and toric varieties, which are equivariant compactifications of tori. And by compactification, I mean partial. So just to give you a hint of why we expect that one can prove such results with this method. So this is okay. And this is, again, a paper with Yuri Tschinkel in Duke in 2012. And this is in progress. So the picture is we have a group G, which should be an algebraic group, which acts, which is contained in X, which will be a projective equivariant compactification. So there is an action on, maybe I should write this. And then we have the boundary divisor. So here we assume, just for simplicity, that X is smooth. And boundary divisor xg, which is x minus g, is has normal crossings. And I will take for u something which is in between g and x, u, which is g stable open subset. This will be the picture. And the example about over there, Pn is an equivalent compactification of the additive group Ga to the n acting on it by translation. And the divisor at infinity is stable. It's just and in that case, if I start from this compactification, there is nothing more that I can, no more examples, but I could take more complicated compactifications and get more examples. So what is this Fourier-theoretic method? As you probably all more or less know, it's interesting to attack this question by introducing the height zeta function. Which will be just the sum so S will be a complex number. So I will take points in G of F, and I will assume that they also belong to, they are also integral, and that the height is smaller, nothing, and of height of X to the minus S. So this is the generating series. And so because there are only polynomially many points of height smaller than B, this Dirichlet type series converges for a real part of S large enough, and it defines a holomorphic function in that domain. And the goal now will be to find a suitable meromorphic continuation of this holomorphic function, and to identify the rightmost poles, and then to use Tauberian theorems to recover from the analytic behavior of this function the behavior of the rational points. But so if we get this, what we can do is to write this as the sum over all point in G of f of h of x to the minus s delta u of x. And this is just one if x is in u of OF and 0 otherwise. And now the point is that this function can be written as a product of functions, of local functions on local fields. And so HV of x essentially is just so there is a section which I will call F, maybe which is H0 of and the divisor of F is, I'm sorry, this is not the right D that I should take. So now there are two Ds. There is inside, I do not take U n'importe comment. I will take U, which will be X minus some, so D will be a sum of d alpha for alpha in A, and U will be sum for some alpha not belonging to alpha U of d alpha. I take it as this form, and so this divisor will be du. Say. This is and the divisor of F is just sum is just U. To do that, I take just an n form on the group, and I look at how it works at infinity. So here I have something which is just HV is something like norm of f of v to the x, and delta v of x is just the indicator function of u of v. And so the point is that I am summing on the f rational points of G a function which is a function on the adelic points of G. And now we are in position to apply the Poisson formula. Which we say that this function, at least if real part of S is large enough so that all the hypotheses of the Poisson formula are satisfied, but this will be an integral over the, so G of F is a closed discrete subgroup of G of F. So this will be the integral on the characters of G of F which are trivial on G of F. Of the Fourier transform of this function, a product of HV to the minus S delta V at the character chi and d chi. So it's just the analog of the formula that says that if you have a function on the reals which is belongs to the Schwarz class or which is L1 and slightly more than L1, then it will be just the sum of C f out of C. with constants. Here depends on the normalization of the usual Fourier transform. But that's okay. And so now this term. So we have this integral. And here it's a product of Fourier transforms. And the goal at this point is very clear, because one needs to understand. So first of all, the Fourier transform, the local Fourier transforms. Understanding the set of real of complex points S, for which everything converges, and the meromorphic, getting holomorphic and meromorphic continuations. We need to consider the product of such. And so typically this will be holomorphic up to some constant sigma prime v of chi v, and this will be holomorphic for S greater than some sigma v or sigma of chi, which will be smaller than the infimum of that, and sometimes strictly smaller. For toric varieties, this is 0, and here we get 1. And then we need to integrate over the characters. So we have meromorphic functions, and we make this integration at a point where it is holomorphic, but now we try to use the fact that we are integrating something which has a meromorphic continuation to get a meromorphic continuation of the integral. This is basically what is needed. There are cases where the picture is easier than another, and for compactifications of additive groups, these 3 steps can run quite smoothly. And so this was done with Yuri, and here we get. Well, I forgot the numbers, but the point there is that this integration is just a summation of a discrete group, and basically only the constant, the trivial character bothers the most. That part can be done in quite a great generality, because it just amounts to some stuff which is known in algebraic geometry under the study of log canonical thresholds. Canonical thresholds. So it's very, it's quite, there are standard methods to understand these integrals. This is a matter of understanding Euler products. And it is at this step that the normalization, the convergence factors of measures come in and so on. And here it's pretty much dependent on the group you're looking at. And when I said algebraic group, you should add, I've used the Poisson formula, so it's only a commutative algebraic group. And if you want to study a non-commutative algebraic group, then you have a spectral decomposition, but it is more complicated than the sum of characters. But in principle, you can do that, and there are papers by Tschinkel, Taklu-Bigash, Shalhaika, and Tschinkel, and the same, who treated nilpotent groups or semi-simple groups, and also a paper by Tschinkel and Tanimoto that treats, at least partially, the case of the AX plus B group, the semi-direct product of GM and GA. And so I have 10 minutes to tell you something about toric varieties. So if you Then so if we do the analysis on toric varieties, so we take will be a torus. So G will be T. And then there is a group of characters. So the algebraic characters and the co-characters. So this is just z to the z to something. And I want to and so x minus g will be a union of divisor d alpha. And these d alphas, which are the boundary components, they form a basis of the group of divisor on x, which are linearized with respect to t. So let's write t. And there is an exact sequence that relates divisor supported by the boundary, so linear combinations of boundary divisor. You can map that to the Picard group of x. Inside that, you have naturally the character groups. Here you have 0. And here it's almost surjective. There is some h1 of f m characters. Let's write m bar, but which is a finite group. And the point in the method is that this behavior, this computation of this high zeta function, you can study it not only for the canonical line model, but also for any line model so you get naturally something which is in a natural extension of this function with some s which has components s alpha, and you make the similar formulas, and you get zeta of s. So, and what you get for the Fourier you get something which is roughly a product of L functions. And here it will be of, say, S alpha at a character chi, at some character chi alpha, and there is a relation between this chi and this chi alpha. And you have also something for the boundary components. And so this will be V finite. And for V Archimedean, we get something which is a summation over all, say, faces of the Clemens complex of something which is roughly a product over alpha S alpha, times something, which is something of this form. And I neglect the chi and so on, but something. And if we look at the analysis theorem that allows you to start from these meromorphic functions, because they are obviously meromorphic, and to integrate them on the character group of the torus which are invariant on that, it means that you have to look at this function, which will be, say, I got a nice notation. So let's say g of s, and we have to do something like integral of g of s plus em dm, and on mr. So we have to integrate this function, which is meromorphic, along vertical lines or vertical spaces, which correspond to M. And in the case of complete toric varieties, what happens is that this map here, inside we have the positive divisor, which are T-linearized, which is just a simplicial cone. So this will be something like R to the A, and this will be R plus to the A. And the image of this is just the effective cone, at least in the real. And here we have the real. And it's very crucial in the analysis theorem of Battireff and Tschinkel that allowed them to prove the case of projective toric varieties, that the image of this M inside does not meet this positive cone outside of 0. And now I can show you some toric varieties in the case of integral points where this does not work at all. So for so that MR is and so for integral points, no more true. And what does this mean? It means that so if you apply the analysis theorem that is implicit in the story to such functions, you will get a contribution which is supported on the Clemens face A, which is an intersection of some components at infinity, which will mean that there are points that converge points of Van Height, so there are points which go to this space. But if the hypothesis of the analysis theorem does not hold for this stratum A, it will mean that the contribution of this space may disappear and not contribute to the analysis, and you may not have points that go there. And what does it mean? What is this obstruction? It is having some M in M minus 0, such that M alpha is always non-negative for the alpha which belong to U, and cup A, and so I have this U, and so it means some M whose components are positive on all the M alphas are the components of M inside diff Tx. And so it means that it is a function M, in function Km, yeah, M over. Gm, and it means that the divisor and so it means that that's a function that's a function which is not that's a global function on U, a character on the torus, and it is regular on the stratum of the face A. And those A should not contribute. I have maybe two drawings to make. And so that was the obstruction in our proof, in our tentative proof of the theorem. And then I showed that to Florian Wilsch. And Florian Wilsch constructed an example, which was in P1 type P1 type P1, with some blow-ups and so on, where, first of all, this obstruction appeared, and then he could prove by hand that the number of points of bounded height was not as we naively expected, but that these faces really did not appear, and could prove that. So then there was an example of Florian Wilsch, and then in discussions with Florian, we understood what this obstruction means, because imagine you have points psi n in G in U of F intersected with G of F, and then we can compute Km of psi, and Km of psi will be, maybe let's try to, F is Q, so Z and Q. So this will be an integer and a non-zero integer, because it's a character on the torus. And so it's at least 1 by the fundamental theorem of number theory. But if you have points psi n that converge to a point psi at infinity, it cannot live on d alpha if m alpha is strictly positive. Maybe it could live on d alpha, but it cannot live on the other components. Because on this d alpha, the algebraic function Km vanishes. So this is a new obstruction. And to get a clean theorem for the number of integral points of bounded height, we need to sum up all these contributions. And when for the moment, we are not in position to give you a satisfactory formula that would be quite meaningful. But it's easy to show on examples already on the plane, and we should have done that earlier, but that's why we need some help sometimes, that all cases can appear. So if we start from P2, P2 is this fan. And then I will write in yellow, this is the divisor that remains. So I have removed the two other components. And then there is a maximal phase corresponding, this is a maximal phase of the Clemens complex. And it's easy to see that there is no obstruction in that case. And so we have the expected behavior. But we could have blown up the intersection of the two lines in P2 and look at these examples. And then this phase, maximal phase, has an obstruction because there are functions which are positive everywhere and strictly positive there. And so this phase does not contribute in this example. And there are examples where we can do a similar thing, which is taking you like this. Again, the blow up, but I blow up in the other direction. I blow up here. And then this phase is non-obstructed, but that one is. And so to get a correct theorem, hopefully correct, we need to look at all these contributions. And the point is that when you have obstructed faces, it means that in the analysis theorem, you can integrate over full lines without getting new poles and so on. And that gives for the final theorem something which is a fibration given by those functions. And the limit measure will not be something like Tamagawa, but a sum over the base of Tamagawa and the fibers. And this is the part we have not written out properly yet, but that's hopefully for the see you in 10 years.
Okay, thank you for the exciting talk. Any questions or comments or remarks?
Thank you. So I guess the first question is, does it work?
Yeah, but maybe you need to put it closer to your mouth.
Okay.
Yeah.
The first question is, so the prediction that is in your paper on the archive on toric varieties.
It's wrong.
Okay. does it hold in some cases? For example, non-obstructed?
Exactly. If there are no obstruction, it holds.
Okay, so
because then the proof.
I see.
So, for example, if there are no global functions on U, if no characters extend as functions on U, then it's clear that there is no obstruction because, and in that case, it works.
Is my understanding correct? If I understand that this obstruction is pretty geometric one, it does not depend very much on the action of the Galois group on the.
No, it's geometric. Yeah.
Okay, thank you.
So this kind of obstruction does not appear for vector group compactifications.
No.
Why?
Because if you good question. Essentially, because linear functions have pole at the boundary, and or almost always. So some do not have, but then in our proof they appear as in the case of additive groups. So we need to look at how linear functions on the additive group behave at infinity, whether they have poles or not. And if they don't have poles, so which is a kind of this obstruction, then the corresponding terms effectively give poles of lower order on for the zeta function. But fortunately, there are always points on parts of the correct order. So.
Okay, so further questions or comments?
This is a naive question, but I think you just answered it. But so the point of these obstructions is that you have a much clearer picture of how to compute the order of the pole of the zeta function. That's the
exactly.
And okay.
So so if there is no obstruction, the order of the pole on the part that comes from U, you just have the rank of the Picard group of U, and you add the number of components appearing in the face, in the maximal faces, and you subtract the rank of the rank of characters. But if there are obstruction, then you need to take out everything that contributes to the obstruction. So you have a smaller part of div U plus A minus a smaller part of the character groups.
Okay, so there seems no further questions. All right. Then thank the speaker again.
Thank you.